Hello and welcome. I hope you are having a great day. In this video, we are going to understand Newton's method of optimization. Okay, so this is what we are going to understand. So this is another gradient-based gradient-based approach for solving optimization problem. So we know what is a mathematical optimization, right? We have covered that in the last video. So this is another gradient-based approach. What is one more gradient-based approach that we have learned? That is our gradient descent. I mentioned in that video there's another approach and we'll discuss this. So first of all, let's understand an issue with gradient descent. What is the issue? Say for example, I have this. So this is your, and we have one big parabola. Okay, something like this. So in gradient descent, what do we do? Say for example, if we are moving from here, you take a tangent at this point. Okay, and that will give your slope. So you move in this direction and then you come at another point. So you move in this direction, you come at, okay, this will give you the direction of the slope, and you go to the opposite direction. This is a positive slope here, so we'll move in the opposite direction of the gradient. We'll come down here at some point based on your learning rate or step size. So you come here, then you take another gradient, okay, and what, depending upon the gradient, whatever is the magnitude of that, you take another step, okay, and you come here. Say for example, now you come very close to this, so you have come to this point, okay, somewhere here. If you see, if you draw the gradients here, right here, if you see, the gradients are very small, so this angle is very small, and if you keep coming very close to, if you keep coming very close and close, right, so these gradients will become very small. So this, if the learning rate it was fixed, it was taking big steps. Now the gradient was very big here, okay. Now as you come close and close to the minima, this gradient will become very small, because it will approach, it is approaching zero now. Here at minima it is zero, right? It will become very small. So now this will take very small steps here, and the convergence will be very slow, and it will not even reach the exact optima. It will reach at some in the some range delta of this, okay. It will not reach the exact optimum depending upon our learning rate, whatever it is. So because of this algorithm getting very slow near the optima or the minima, okay, this is the problem, because it is dependent on just the gradient of this, and the gradient slowly, this is a very steep gradient, and slowly this will decrease as it comes closer and closer to zero, and that's why your convergence will be very slow. So this is a problem of gradient descent, and for solving this we use what is called Newton's method. So what Newton's method does is that at every step, okay, I have drawn a diagram already. So at every step, what it does, instead of just taking, so this is a slope, so it will know the slope, and it will also take the second derivative, okay, f double dash x at this point. So what does your f double dash x give? It gives the curvature, in which direction the curve is curving now. It also gives me the curvature of that. So f dash x gives me the slope, that gives me the straight line direction, in which direction it is moving up or down. But f double dash x will give me the second derivative. It gives me the curvature of that curve at that point, okay. And using that curvature, if I'm going down, I will create a parabola. I will use the curvature. I'll create the parabola. So this is like going down a valley, and I know that instead of going just in straight lines, I also am getting the, in which direction it is moving. I'm getting the curvature of the slope, so that I go to the minimum. So I'm also using the curvature, in which direction. I'm not blindly just going down, okay. So I'm also seeing the curvature, and depending upon the curvature, I'm taking my next step. Earlier here, so the learning rate eta, okay, this eta was fixed, we fix it, or we can change it also, but generally considering that this is fixed, it will take those steps and it will multiply that learning rate into the gradient that it has received. Here in Newton's method, what it does, it will use the gradient, and the learning rate is decided by the curvature, the second derivative. So your Second derivative f double dash x is it gives the curvature at any point, at point x. Means at x, how the function is curving here, and I will use that information, okay, and I'll draw a parabola at that point. So at this point I'll use the curvature of this, I'll draw a parabola at that point, and I'll go to the minimum of that parabola. So this is my minimum of the parabola, and now if you come back to this curve, so you have reached here now, okay. So now at this point you have reached here. Again at this point, using the curvature of this, I'll create another parabola, and I will go to the minimum of that parabola, reach here, and then go to the bottom of the parabola, and this will give me the next point. So now if you say, see, without the learning rate, just using the gradient, and I'll also create the calculate the gradient, and my learning rate will be coming from the curvature. So the more the curve, the faster it will move. And as you see, like if you come closer and closer to this, right, so the curvature will increase, the curve. And if it is a curvature, finally if the curvature is exactly quadratic, this is a quadratic equation only, but if it is a higher order polynomial or something, then it will directly move to the minima or optima. If it's maxima, then it will directly move to, in this case minima, it will directly move to the minima. So if you see how it is coming here, then jumping here, then again I take the curvatures information plus the slope, okay, slope, even if the slope is decreasing here, okay, and the step size I'm deciding it using the curvature, so I'm using more information from the curve, and that will give me. So if normally if I use this instead of the gradient descent method, okay, which takes step size which is computed, if I use this Newton's method, it converges very fast in very few steps it will reach the minimum, okay, compared to gradient descent where I have to find an optimum learning rate, okay, by doing some trial and error and then getting that right. This Newton's method will directly give me that, because it is in the curvature, it will give me very fast convergence to the minima, because at every point it is just creating these parabolas and it is just going to the bottom of the parabola, the minimum of that parabola now, okay, and then it is just going to that point, okay, and this is how it is giving me very fast convergence towards the minima. And that is the problem that Newton's method is solving, and this is what it is giving. So as I mentioned in the last video, so this is your gradient descent, okay. Gradient descent uses only, what was the, okay, first order derivative, it uses only f dash x, it uses only first order derivative f dash x. Newton's method, it uses second order derivative. So if I have to go to the new point, right here, what was the gradient descent? So if I have w new is equal to w old minus learning rate into f dash x, say for example that was the loss function, right, dou L of loss function by dou w at w old. So I was just using the first derivative. What Newton's method does is, say for example I'm moving to the next point xk plus 1, I'm giving you a simplified view so that you understand what it does. It will do the old point, that is, say for example this is x new, this will be x old minus f dash x old by f double dash x at old, okay, this is your x old. So it will compute this, okay, and because of this information, so this f dash x remains as it is, and this eta has been replaced by inverse of the second derivative, and this is your learning rate now. So now this is being controlled, so the step size can be controlled depending upon the curvature. The larger the curvature, because the more curved, so here it is like a straight line, here if you see it is more curved, it is like a circle, the circle will be like very curved. So here it will be coming, okay, it is becoming more and more curved, so I will take bigger steps here, okay. So my curve will, I will use the information of the curve to move towards the minima, and which was not happening if I just use the gradient here, because the gradient will gradually reduce. So just using gradient information is not helping, and that's how this is becoming very fast, okay. So it is also using the second order derivative. So what is your Newton's method? Let's formally write it. So now you have understood the concept. Okay, so this is nothing but it is a second order derivative. Derivative, second order derivative gradient based based iterative. It is also iterative method. Okay, used for optimization. Here I use both first and second derivative, and it is known for its extremely fast convergence, because we saw how it is jumping to the next point using just by creating the parabola and jumping to the bottom of the parabola using the curve, and then it just comes down 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 down. This is why it's so fast. And this achieves, so as it reaches here, right? So I have explained this. As it reaches near the minima, the gradient based gradient descent method, it slows down, but here it uses the convergence, the quadratic convergence, and it closes. Okay, it comes very close to optimum very fast. Okay, so let's write the algorithm for this. So extremely fast convergence. So how do we write algorithm for this? So I have written this already. I'll just copy. Okay. So I have a note for this, and I'll explain this. So I have taken this, and let's understand this quickly. Make it simple. Whatever you have discussed, we'll just do. This is the algorithm. Okay, let's bring it down a bit. I hope this is readable. So this is your algorithm as we had for gradient descent. So you start at any random point. So this is your random point. Let me use another color. This is your random point. Okay, and you compute the slope, how tilted the curve is, and you compute the curvature at that point, xk, how tight the curve bends. So it will give me the curvature, and then draw a parabola that locally approximates the true function. So at each point, I'll draw a parabola that locally approximates the true function. That if this is the curvature, what will be? If it should be like this, right? So if this is the parabola, I will be like this. This is a parabola, I'll be like this. This is a parabola, I'll be like this, and this is a parabola, I'll be like this, right? So and go to the jump directly to the minimum of that parabola. That's your next step. Okay, this is the algorithm. So instead of walking down the slope step by step in gradient descent, you are jumping straight where the curve bends downward to the bottom, and then you just iterate till you convergence. Okay, and you just repeat until convergence, and that convergence will be very fast. I hope this is clear. So that's the, if you have understood this diagram, what it is doing, this is what is the genius they have used. Newton has used long back that I can use the curvature also. This is also called Newton-Raphson method. Okay, so this is for a simple univariate. So, but I have for a multivariate case, if you have multiple variables, how does it go? For multivariate, so you calculate the second order derivatives will become the Hessian. Okay, so we'll use the Hessian here. So what will be the update parameter equation become like? So this will become multivariate case x new is equal to x old minus, so I will use the del square f at x old inverse. So this will be multiple variables, so this will be your Hessian. Okay, this will be a matrix of all the derivatives. So the diagonals will be second order derivatives, and the These will be partial derivatives. All will be partial derivatives only, but that will be mostly that this is symmetrical. Okay, and then this will multiply to the del of f at x old. So here this is replacing your learning rate, and this is your same thing. So just the learning rate is replaced by the negative of your second derivative. Okay, so what is your new step? This is your nothing but, let me write, so this is nothing but your Hessian inverse, and this is your gradient, and this Hessian inverse is also your step size, which uses the curvature. You draw the parabola and keep jumping. Okay, I'll give you a simple example, but it will make more sense for higher degree polynomials, but I'll give you a simple example to understand how the math works. For example, we have f of x is equal to x square minus 4x plus 5. Okay, so how do we do in a normal way? Okay, so we have to find the minima for this. Okay, whatever is the minima. So f dash x will be 2x minus 4. This implies x, the optima will be at, you equate 2x minus 4 equal to 0. This implies the optima is x star equal to 2, means there is some optima. And how do we test whether it's a maxima or minima? We take the second derivative, this is equal to 2, which is greater than 0. This implies that this is your and this is your minima. Okay, simple. So this is for univariate case. You can take the second derivative, you can consider this as a Hessian. Okay, if you don't understand what is a Hessian, you can check the matrix calculus video. I'll put the link in the description. So now let's solve the same thing using Newton's method. So using Newton's method, if I solve the same thing, how will it be? So what is this? Okay, so now I'll apply the algorithm. Okay, so let's start. So let's start at x equal to 0. Okay, and what will be my x new? Equal to x old minus Hessian inverse, I'll write in Hessian terms, into gradient. This is equal to x old is 0. What is your Hessian? That is your second derivative. This is nothing but your Hessian, right? Equivalent to Hessian if I am writing in Hessian terms. Hessian is for multivariate, but also this you can, just for the definition's sake, we can write oversimplified way of saying this. Okay, so if this is your Hessian, its inverse will be reciprocal of that in number terms, 1 by 2 into, what is the gradient? 2x minus 4. So 2x minus 4, you put x equal to, okay, and this is for this is at a gradient at x equal to 0, right? This is equal to 0 minus, so I'll leave that. This will be minus half into 2 into 0. This will be x equal to 0, so 2 into 0, that will be minus 4. Minus 1 minus goes off, 2 goes off, that is equal to 2. So just in one step it will reach, if I am going stepwise. If you go gradient descent way, then you will calculate the, and then there will be a step, right? If it is 0.01, then slowly it will converge if you calculate the gradient at each step. Here just in one step it has reached the minima, which is your x new. That's what I wanted to show you, and you can calculate the same thing using gradient descent. Okay, but this is very fast, works very fine, very convergence is very fast. Okay, but there are some limitations to this, so understand the limitations, why it is not so famous in practical machine learning. Okay, directly you will not hear Newton's method being used, so there are reasons. Okay, what are the limitations? So the first limitation is the Hessian inverse calculation. Hessian inverse calculation. So this is, okay, this is the, for a n cross n matrix, right? So this is for a square matrix. So for n cross n matrix, the time complexity for calculating this Hessian inverse is order of n cube. Okay, very high. And then if we have like just calculating the second derivative, right? So if you have to calculate the second derivative, that is the Hessian for that function f, okay, so that will require, that is this time complexity is order of n square. So these are very very high time complexities. And then there's one more reason. If you're using a Hessian, right, so this, if in case if you're going down the curvature, right, if you're going down the curvature here, so the Hessian can also give you a saddle point. So if you encounter, so third point, if you encounter a saddle point, if you encounter a saddle point, so the saddle point can have a minima and maxima on both the cases can be there, because it is minima at, and along one variable, maxima along other variable. So if you encounter a saddle point, you can hit the maxima of, okay, so you can go towards the maxima of that variable, and that way you will not converge fast. So that will not give you the convergence, or you may go to another path to altogether. Okay, so it can go to the, it can go to maxima in other direction. That is also optima, right? Maxima instead of minima. So you want to go to the minima, but these are both optima, so it won't differentiate and it will go towards the maxima of other direction, other variable, and that's what will cause problems. So these are the main these things. So in modern day machine learning, right, so where we have millions and billions of data points in a data set, calculating the Hessian for such big data set, which is order of n cube, is like very prohibitively expensive, very very highly expensive. It is prohibitive. Okay, so this is highly expensive for like 10 to the power 6, 10 to the power 9 data points. That is common for machine learning, okay, for deep learning at least. So that's what discourages the use of Newton's method. So the question is, it is very good. First thing we can, then we said, okay, there are so many limitations that it makes it unusable. So is it being used or not? That's the question. So is it useless? So no, it's not useless. So some quasi-Newton methods are used, okay, which are not exactly quasi, the approximation of it. So what do we do? That so we use, say for example, we use gradient descent here, and as we approach the lower ends, right, here we use the Hessian, sorry, the Newton's method, not in the complete. So here, and also for calculating the Hessian, right, calculating the Hessian inverse, which is order n cube, we use some approximations. Okay, we use some approximations like low rank approximation, using the older data to get some good approximation of the Hessian at that point, and because of that this time complexity is reduced, and then this becomes usable. So this is not actually Newton, but a quasi Newton method. And the some famous ones are, for example, so there's like so there's a quasi Newton method, quasi whatever they say, and then there is something called BFGS. Okay, this is name on the on of 4 scientists are there, so you can search that. That's called Broyden, Fletcher, Goldfarb, and Shano. So this is coming from Broyden, Fletcher, Goldfarb, and Shano. So these are name of the scientists who invented this quasi, okay, which is used as Newton method inside it. Okay, and then there is a one more enhancement of this, that is called LBFGS, which is limited memory, because it this limited memory. So as you see, this Hessian calculation can take order of n cube, so this can take a lot of memory. So they use some approximation to use limited memory. So there is some enhancement on top of BFGS, and this is called limited memory BFGS. So that is the application in modified form, not exactly, but some form of Newton method inspires some other algorithm, and it is being used then. Okay, so that's all for Newton method. Let's quickly do a revision. So what was the problem? So the first problem was, we in the gradient based approach, So if as we reach in gradient descent, right, as we reach the minima, the gradient becomes very very small, because finally it will become zero. So at this point it will be very very small, and if you're taking small steps here, eta is very small. So the convergence will not go to the exact value also, it will be very small, it will stop somewhere before convergence. Okay, it is so small because we'll iterate till certain point. Okay, so what Newton's method says that is that instead of using just the gradient, that is first derivative, why not use the second derivative also, which gives me the curvature of that point. So using the curvature of at that point, you draw a parabola, go to the minimum of that parabola, and take to the next point, move to the next point. So now I'm also using not only the gradient but also the curvature of the curve. Using that, I'm moving very fast downhill now, because I'm using more information from the curve, and that causes very fast convergence, especially when it is quadratic, or it becomes, whenever the function becomes quadratic at certain point, it will just converge in one step. It is so fast. Okay, then we saw the algorithm. You start at any random point, you can compute the first derivative, second derivative, then you draw the parabola, whatever you have said, and then you jump at the minimum of the parabola. Okay, and how do we update the parameter? So this new parameter is old minus, this is the Hessian at the old point, inverse of that, and into the gradient. And this Hessian is nothing but acts as a step size. So now explicitly you don't need to have a step size. Using the curvature, it will calculate its next step, and that is what causes the fast convergence. Okay, this is nothing but Hessian inverse, and in simple terms we saw that this is nothing but x new is x old minus f dash x by f double dash x. Okay, and in matrix terms this becomes inverse, which is your second derivative is nothing but in a multivariate calculus, this is your Hessian. Okay, and we saw a simple example, and then we saw some limitations, that even though this is the convergence is fast, everything is very good, calculating the Hessian inverse is a very costly affair. It's of order of n cube. Similarly, calculating the Hessian is also order n square. And there's one more issue, if you encounter a saddle point, if you're using the Hessian, right? So instead of going to the minima, it can go to the maxima of the derivative. Saddle point is that only, right? It can be minimum with respect to one variable and maximum with respect to that variable. So it can go to the maximum, and then the convergence will be all messed up. And then this is very costly for large data sets, which is very common in deep learning or new learning machine learning algorithm. So is it totally useless? It is so expensive? No. We use this inspiration to optimize the other algorithm, and there are some quasi Newton method or quasi Newton method, okay, that is being used. For example, the gradient descent, when the mixture of it, when it approaches the minima, right, then we can use the second derivatives. Okay, this approach can be used, not in the complete algorithm. And then use some other forms of which you employ some other form of Newton method, which are called BFGS, which is based on the name of some 4 scientists. And there's LBFGS, which is limited memory BFGS. Okay, I hope Newton method is clear. It is very important. This gives you one more way, okay, that how approximations, or how you can come down and you can convert very fast to the optimum minima. Okay, so on that note, let's end this video. Thanks for watching this video. Have a great day ahead, and bye for now.